All right. OK, thanks a lot. Thanks for inviting me. So super excited to be here. So just like Richard, I made the title of the talk a while back. I was like, I'm going to talk about going beyond like theory of mind, which is a way of modeling interactions. I was thinking I'm going to talk about that and conventions. And then it was like almost like last night. I was like, oh, I need to make this talk. It's a new talk. So I should actually start putting things together. So it's a new talk. The transitions are a little rough. Some of it is older material. So just wanted to give that heads up. So I work on human-robot interaction. And in general, I'm very interested in understanding how humans interact around robots and how robots should actually respond to humans. And I usually talk about the problem of trying to model humans doing imitation learning or learning reward functions. So that's the usual type of things I'll talk about. I think Anka talked about that a couple of days ago. So I'm going to skip that and today talk about interaction. So when we think about interaction, usually the common thing that comes to our mind is human-human interaction. Humans are really good at this. They easily come into each other's spaces. They collaborate and coordinate with each other on really complex manipulation tasks. And another thing that they're good at is they can influence each other. They can take actions that can actually influence the other agent for the better good of themselves or the team. And they do all these like crazy like coordinations that goes on in various sorts of tasks. And we see that in cooking. We see that in sports. We see that in driving. And ideally, what I'd like to do is I'd like to be able to build a robot that can come in and collaborate with humans and do the type of task, have the same sort of seamless collaborations that we see humans have with each other. And that's really difficult because robotics is hard, and Ross talked about that. And as you can kind of see a trend, like robotics is really like cooking, so they keep like bringing up this cooking problem. But in addition to that, the other issue is actually dealing with interactions. And you kind of you can see that in a few examples that I'll mention later in the talk. So how do we model human-human interaction or human-robot interaction? So the common way of thinking about interaction, a human-human interaction, is by using this idea that's basically we're playing a game together. You can think of it as a game of chess where it's competitive, or you can imagine a setting where you're solving a collaborative game with another agent. And then usually the way we think about interaction is that this person who's trying to make a decision here should take actions based on the actions of the partner. So what it does is it basically tries to have some sort of model of the other agent, have some belief over the state of the other agent, some belief over policies of the other agent, or some belief over the belief of the other agent. And that can blow up really quickly. Like if you're talking about beliefs over beliefs, that is infinite dimensional. You cannot even like represent that. But usually, like ideally, that's what we want, right? If we were to like model this right, we think this idea of the actions of this person and how it should depend on the actions of the other agent and how it should think about how the other agent responds and all that should be the right way of going about it. And that's actually called theory of mind. So if you think about this person making decisions just based on a one level, like decision making of the other agent, that's called the second order theory of mind. If you keep going further, that's nth order theory of mind. Okay? And today, when you think about human-robot interaction, most of the work tries to do the same thing. It tries to think of this collaboration game that's going on between the agents, making a puzzle, and then robot thinking about what would the human do, human thinking about what would the robot do. Okay? And then we actually did that ourselves. So like one of the problems that we looked at was a driving problem. So this was back in my PhD, where what we did was we looked at planning for an autonomous car. Let me go back to this slide. Planning for an autonomous car, that's the orange car, based on how the other person, the human-driven car, responds. So we're basically thinking about this interaction between the two agents here as a dynamical system, where we're saying, hey, like I want to plan for this autonomous car. The actions of that autonomous car should be UR star, which is a maximizer of a reward function or some sort of objective of the autonomous car. And that should depend on the actions of the autonomous car. But it should also depend on what the human does, right? Again, theory of mind. It should depend on what the human does. And that's kind of this term here. Okay? And well, what does the human do? So a big thread of my work is about what does the human do. But right now, assume that the human is optimizing some sort of reward function. So assuming that there's some underlying reward function that the person is trying to optimize, then we can say, well, the person is optimizing this RH. And that also depends on the actions of the human, UH, but depends on the actions of the robot too. Again, theory of mind. Okay? So we actually tried to address this problem, and there are a lot of interesting questions here. And solving this is really hard. Solving theory of mind is really hard. It's computationally really expensive. So what we ended up doing was we ended up making a set of approximations to be able to run this on a vehicle. So the approximation was, hey, they're not actually doing theory of mind. Let's solve this as a stack overbreak game, as a leader-follower game. And what that means is I'm going to cut the game at the second step and don't think about this infinite recursion that happens. So what we assumed was the actions of the autonomous car influences the actions of the human, but the human is observing the actions of the autonomous car. And we just ran that, and it kind of worked out OK. We ended up getting behaviors that were kind of fun. We ended up getting this behavior where the autonomous car would nudge in front of another vehicle and make it slow down. Which you might say, well, why would a car do that? But it's actually a reasonable thing to do, especially in LA area, right? Like if you're driving on 5 or 405, like you're going to cut in front of someone and influence them to slow down. So we saw these influencing behaviors, which was kind of exciting, because we actually started like thinking about interactions. All right, so that's theory of mind. But I'd like to argue that when we think about human-robot interaction or human-human interaction, most tasks that we are dealing with are not playing chess. Like most tasks that we are actually dealing with when we think about interactions in our day-to-day interactions with other agents have nothing to do with that. They're kind of tasks that are like this. So imagine you have a collaborative construction. You want to build a building. If you're building a building and you have a partner and you've been working with that partner for like a long period of time, at every point of your day, you're not thinking about, hey, what is Bob thinking, and how should I respond to Bob's actions, right? You have a set of conventions and rules, and you quickly figure out what the other agent is really trying to do. And that's kind of interesting, because we know humans, like one thing we know about humans is that they don't have infinite computation. They're bounded rational, right? Like that's like one of the few things we know about humans. So if they're bounded rational, there's no way for them to like store this belief over beliefs, right? They're not going to store that. Instead, what they're doing is they're keeping track of almost like low-dimensional representations. And based on those low-dimensional representations, sometimes they're shared representations, they can achieve these collaborative tasks. So I want to argue that the correct framework to think about this is really not the theory of mind. Instead, we should think about this shared representation that the two humans in a collaborative tasks is sharing. And it's a good question to ask, well, what is that? What is that shared representation? But one thing that we at least know is that shared representation has a set of properties. It's a low-dimensional representation, because they're not going to store a giant thing. It's something close to a sufficient statistic, because they can do the task based on that information. It can change over time, because humans tend to adapt to new people and tend to get used to different people. So it has a set of properties. And what I'm calling this shared representation is conventions. So I'm going to use the word conventions throughout the talk to refer to this low-dimensional representation that exists between two humans. Okay? And ideally, if I'm building a robot that's supposed to be interactive, that robot should also have access to this shared representation and try to plan based on that shared representation. So as I said, I'm calling these conventions, and I'm more formally saying conventions are low-dimensional shared representations that can capture the interaction, and they can change over time. Okay? All right, so under this definition, I want to answer a few set of questions and try to do interaction better. And specifically, the questions that are interesting here is, when we think about human-robot interaction, well, what are conventions? Like, what is a convention for a specific human-robot interaction that we are thinking about? Can we communicate them? Is there an easy way to communicate conventions? And can robots, if I can't communicate them, can robots directly learn conventions through interactions with humans? So basically what I'm proposing is robots, instead of having this theory of mind idea and planning based on their knowledge of what they think the human thinks, they should just learn conventions and use that for planning. And then finally, which is something that I'll probably won't get a chance to talk about it in details, I'll just mention it towards the end of the talk. I think another interesting question to ask is, can we influence conventions? So if I have a particular way of doing a task with a human, and I have another way of doing a task with another human, could I take my actions in a way that I get one of them, like with a new person? Like, could I actually manipulate conventions? which is a little bit up in the air idea. Like I'll talk about it later and about like what exactly I mean by that. But that would be kind of fun to do. All right. So okay. So that's the plan for today. So okay. So what I'm going to do today is I'm going to talk about two different settings that we think about when we talk about human-robot interaction. The first setting is when there is a human controlling a robot. So there's a robot agent at the end of the day who's doing all of the tasks, and the human is really just teleoperating the robot. So the human is actually interacting with this robot, but just through a joystick or through some sort of interface. And the second case is probably something that's a little bit more familiar, which is the human and the robot are kind of symmetric, like agents who are interacting with each other in a task. So human takes a step, robot takes a step. They're working together on a task. Okay? And I think both of these are pretty interesting. When people talk about human-robot interaction, they usually think about one or the other. And the reason that people do this first one is you can actually do it. This one is much harder. It requires robots working well. So that's a big requirement usually. So that's why I'm going to first talk about some ideas around teleoperation and what does it mean for a robot to learn conventions when a human is teleoperating the robot. So specifically, I want to think about, okay, so what are conventions in these setups? And then if the robot knows the convention, could it do the task better? Okay? All right, so let's talk about that. Okay, so why do we care about teleoperation? So I thought, so when I started in this field, I thought, okay, autonomy and intelligence are the things that we should get right, control, that's what we want to do. And I thought teleoperation is just really easy and no one does it. And then actually I remember I visited Intuitive at some point during my PhD, which is this robotic surgery company. And at the time, Ken Goldberg was doing a lot of work on robotic surgery, and he was doing imitation learning and trying to learn how to do stitching and all that. And I went to Intuitive. I was like, where is the automatic stitching system? And they're like, we don't really have that. This is teleoperated. What are you talking about? So I was kind of surprised that robotic surgery, there's no autonomy there. It's a surgeon sitting here, and basically it has two devices. And based on those two devices, 4 things come out, and you're teleoperating them, and you're doing the task through the interface. So there's really no autonomy here going on. But it's still really difficult. So I think it's just an application of where teleoperation shows up. That's one place. Another place that we are seeing teleoperation more and more, in our everyday academic lives today, is collecting data. So another place that this comes up is if you think about things like vision or NLP, they've used lots of data and they've made a lot of advances using ideas from deep learning. We haven't seen the same thing really in robotics. Some might argue that the reason is we just don't have enough data. So there is actually a group, there are multiple groups who are doing similar things, but there's a group at Stanford, so this is Silvio's group, and what they're doing is they're trying to crowdsource the data collection problem. So what they're doing is they're getting different people, teleoperate robots in simulation to do pick and place, to just collect lots of data of pick and place. Okay? So this is another place that we see just lots of teleoperation, and people have difficulty teleoperating these robots, if you look at each one of these videos. And it's also in simulation, so things hit each other and all that too. So it does have some issues. And then finally, the last domain that I want to actually focus on is the assistive domain. So another domain that we see teleoperation a lot in is an assistive robotics domain, where you have wheelchaired arms, and you have the arm, and you would want the arm to do various sorts of tasks in your everyday life. So more than 1 million Americans actually use things like wheelchaired arms, and they use it for things like dressing or bathing or eating. So these are various sorts of tasks that you would want to use your arm to achieve. So here's actually a video of it in action. So we have this JCO arm. It's a high degree freedom arm. And then this person is controlling it. And the thing I want you guys to notice is his hand here. So he keeps pushing the side. So what he's really doing, does anyone know what he's doing? Anyone know? So what he's doing here is he's actually changing the mode. So this robot has 6 or 7 degrees of freedom, and you can't control 6 or 7 degrees of freedom with a joystick with 6 inputs. So what he's doing is he's changing the mode from translation to rotation. So you're controlling X, Y, Z of your arm, and then you switch the mode, and you're controlling yaw pitch roll of your arm. And that actually that's why it takes a lot of time to actually do teleoperation on these arms. And this is called end effector control, meaning that you have the end effector of your robot, and you want the end effector of your robot to go to a new yaw patrol, XYZ location, and then that's how the robot would just implement it. Okay? All right, so that was an example of where assistive robotics show up. And assistive robotic arms are generally dexterous, and this dexterity makes it really hard to actually control these robots. So what we would like to do here is the question of, can we learn some low-dimensional representation, some low-dimensional action embedding to make controlling these robots more intuitive for humans? So what I'm referring to as convention here is a human would prefer a 2-degree freedom control space, would not want to really deal with like this 6 and 7 degrees of freedom. Human would want to control like something that's much lower dimensional. And then by that something much lower dimensional, the robot should understand what the human really wants. So the idea that we're trying to explore here is, could we do some sort of dimensionality reduction on the action space? So could we learn this low degree freedom action space so the human can control the robot arm? And you might ask, well, why is this even possible? Right? Like why is this even possible? If I want to go from any state in the world to any other state in the world, I do need all those degrees of freedom. They exist for a reason, right? I actually do need like all of those degrees of freedom. But this is actually only possible if I know the type of task I'm doing. For example, like if I have an arm that's just moving on a sine wave, what I can do is I can control all those 7 degrees of freedom and get the arm move on a sine wave. The other thing I can do is I can just say, hey, +1 should get the arm go to the right, and -1 should get the arm go to the left. And like that 1 degree of freedom should be enough for achieving the task, given that the task is moving on a sine wave. So I know I'm cheating here. Like I'm saying task is moving on a sine wave. If task is moving on a sine wave, there exists a 1 degree freedom control that could do that task. Okay? So our idea is, when you're thinking about things like cooking tasks or tasks that are in home in a specific like location, conditioned on the states, you could actually bring down the dimensionality of your control space. So more specifically, like what we're really doing is we're bringing an expert. In this case, it's Dylan. So what Dylan is doing is he's showing these expert demonstrations of like high dimensional motions for general types of motions, like sweeping motions or like moving the arm and reaching the arm from various locations. So not specific tasks really, just general types of motions in this workspace. Okay? And then from these high dimensional motions, what we could do is we could actually learn a low degree freedom, low dimensional latent representation for doing like online control of the robot, for going from any location to any other location in this space. So at the end of the day, what I'd like to do is I'd like to have a 2 degree freedom control and then use that 2 degree freedom control to achieve various sorts of tasks in this setting. Okay? Does that make sense? Okay. All right, so what we're proposing is basically, we're proposing we should do some sort of dimensionality reduction here. Specifically, we're using a conditional variational autoencoder with changing the loss function so it satisfies a bunch of properties that we care about in order to learn this low dimensional representation. So specifically, so the set of properties that we care about in this setting is, first off, this low dimensional embedding needs to be conditioned on the state, right? Because I'm saying, like, depending on the state, depending on the scenario you're in, you should be able to have a low dimensional control input. So that's Z, condition on state. And this is my decoder, which should give me the high degree freedom robot action. And in addition to that, I would like to be controllable. So I would like to be able to go from any state to any other state in my workspace using this low degree freedom control space. So that's another property that I would like to have. And another interesting property is more of a continuity property. So another thing that I would like to do is, if I'm pressing right on the joystick and my arm ends up on the right, and if I press right again, it goes to the right, and if I press right again, it goes like on the left or somewhere weird. Like, that is really weird. Like, that's not very consistent. So, and we actually ended up getting that behavior, so we had to put this property in. And what this property is trying to say is you have temporal consistency. So if you're pressing right in states that are close to each other, it has the same meaning. Your arm actually ends up in a state that's right of your current state. And then we also ensure things like scalability, which is basically saying that if I'm pressing too much to the right, my arm should go too much to the right, and vice versa. Okay? All right, so under these properties, what we could do is we could learn a conditional variational autoencoder conditioned on a specific state. And the thing that we are learning is the latent action. So usually when people use CVAEs, they learn the state, right? They do dimensionality reduction on state. What we're doing is we are doing dimensionality reduction really on the actions that are going in the robot. So once we have learned this on the collected Dylan's data, what we can do is we can bring in any other user, and then any other user could use the joystick and put a much lower degree of freedom control and kind of expect reasonable behavior out of the autoencoder. Yeah? Yes?
State something you choose and specify?
So state.
For the arm, you can imagine state being like all the joint angles and their dynamics, or you can just say my state is just the end effector.
You can actually say your state is just an end effector, but you do need to have your environment. So state is also encoding things around like where are the obstacles and where's the object I'm trying to reach and whatnot. And we are actually encoding those values as actual states here. One could imagine having images as a state here, and you could potentially do that from pixels too, but we haven't done that. So
just to clarify, you're trying to constrain the learning so that it satisfies the properties we've seen.
Yes, yeah, those are things that go in the loss function, yes. All right. OK. So we do this, and we actually, I'm going to show just some videos of like how it looks like, and talk about like what we did after that. So what we were doing is we were collecting 7 minutes of demonstrations from the expert. So you can imagine this expert is so your caregiver or someone who knows like how to move the arm, and you're collecting 7 minutes of kinesthetic demonstrations on the robot, and then based on that we are trying to learn these latent actions.
So low-dimensional is one thing, but so you might expect that sort of different axes, so think about joystick, right?
Yeah.
Different axes have sort of independent.
Yeah, that's very true. Yeah, so you might actually get really weird axes, right? Yeah, so what we do is we, after the fact, do an alignment. I'm not talking about that in this work. What we are doing is we're trying to learn the alignment that's preferred by the person too. So after the fact, because you might get any weird alignments there. Yeah. All right. So what I'm comparing now is I'm comparing end effector control, which is what you saw in the first video, which is you have to like switch the modes, versus latent actions, which is a 2-degree freedom control, trying to do the same task. So end effector control, you have your joystick. You either do linear control, so X, Y, Z, or you switch the mode and you go to angular control. You do yaw pitch roll. And then with our approach, we have 2 dimensions, Z1 and Z2. All right, so here, what we are trying to do is we have a task. It's a make an apple pie task, which is not really an apple pie, but imagine it's a make an apple pie task. And on the left, we have the end effector control. On the right, we have latent actions. And I'm going to show this video. So what you can see is on the left, like the person, even though the person has training with this robot, like has a difficult time trying to figure out like how to get to the objects and move them around. But in this case, like it's just like pretty intuitive to like use it. And the task is like it's actually like done much faster using our method, which is actually one of the things that like when we talk to Jaco, like one of the things that people complain about using these assistive robots is how long it takes to achieve a task. So what we try to do is we try to look at these more long-term tasks. And this is actually the combined version of it, which is a more long-term task. And it's much easier using this idea of latent actions to control this robot. So again, like just look at the right, it's so much like smoother than that. So you move the eggs. Those were the eggs. You move the flour, I guess. We did try with real flour for different experiment in the lab. Was not a good idea. And then you bring in the apple. And then we had like a steering at the end, which like no one knew how to do. So we have like the weirdest steering behavior here. But in any case, like that in that setting, like they're still like bringing the flowers. So this was kind of fun. And what it kind of told us is humans in general have this low-dimensional representation, right? This low-dimensional representation, and we should try to figure out what it is that they want. And what we're trying to do here, the interaction was really between the robot and the human in this teleoperation setting, but the interaction was basically trying to get the robot understand what are the conventions that humans are trying to get at. Here's actually the trajectories of that experiment, so you can compare the end effector and our approach, which is much smoother than these. This is like end effector trajectories of what happens from the beginning to the end of that task. So qualitatively, it kind of looks like smoother for our case. But we actually have like values of completion time and success and all that. But just wanted to give you a view of like how the trajectories look qualitatively. So the summary so far, so what I've been talking about is this idea of embedding these personalized behavior through latent spaces, which I'd like to call conventions. And we formalize the properties that these latent spaces need to satisfy in order to just learn them and figure out what people really want, and learn them through efficient amount of data, so through like limited amount of data collected by the expert at the beginning. So that was pretty good. We were happy with that. But the problem there was this was kind of working okay, except for when we were coming to like more closer and more like precise manipulation tasks. So we had another task that I didn't show actually, and this is a task where the robot wants to go and pick up. It has a fork in its hand, and it wants to go and pick up any of these 3 marshmallows. So this is actually a task that's used by other groups too. So I think from Henny Edmoni's group at CMU, like what she has a data set on this called the harmonic data set, and basically the task is going and picking up marshmallows. And then Hung in this case like is using this Layton Actions like thing that we have designed. And what ends up happening is like, I'm going for this. And then he goes like on top, and it's like, oh, is it on it? Is it not on it? Like goes to the side like to figure out if it's actually on it. And then boom, he didn't even grasp it. So when it comes to dealing with some of these more like precise like manipulation tasks, like when they usually like come up in things like feeding, or if you're looking at various sorts of tasks like cutting or scooping, it's actually pretty hard to do them even using this latent action. Even though the idea of the latent actions is a nice idea and it allows you to control things like style, it's still pretty hard to get precise manipulations. So if the robot really knows what your latent actions are, maybe the robot can figure out where you're going for, and maybe the robot can help you in these settings. So what we decided to do next was basically this idea of, sure, there are some conventions. The human really wants to use this low-dimensional action space because they have bounded memory. But if the robot knows that, could it help? Could it do something extra? And this idea is not a new idea. Like shared autonomy is not a new idea, right? People have been thinking about adding shared autonomy on robots. And here, what we are trying to do is we're trying to do shared autonomy based on the conventions that are built by the human. So what I mean by that is the robot kind of starts off with some belief of what object the person is really going for. So in this case, there's a red cup and there's a purple cup, and the robot could be going for any of them, and the human is starting to put input. And then at some point, so at the beginning, this is a video, yeah. So at the beginning, if the robot figures out that, hey, you're going for this red object and its belief goes higher, it could actually add a little bit of control and try to help you do that more precisely. And then once it does that, it kind of releases the control back to you so you can control things like style. So let's say you have like 1 degree of freedom. If you have 1 degree of freedom, with that 1 degree of freedom, you can't really like pick up the object from any style that you want. Right, and any of these objects. So, but with 1 degree of freedom, if the robot at some point figures out you're going for the red cup, it could kind of release that 1 degree of freedom and give it back to you and be like, OK, I figured out you're going for this red cup. Take the control back and tell me how you want to pick it up. And then after that, the robot can try to like give you the right style and how you should pick up the object. So that's kind of what's happening in this setting. OK? So our idea is, OK, so now we have this intuitive embedding. That's great. Could we combine it with shared autonomy to actually do some of these precise manipulation tasks? OK? So how do we do that? Well, remember we had this decoder. What we can do is we can actually put in the belief into this decoder, and then train a decoder based on also the belief that the robot is getting, based on what goal the person is going for. And this kind of works for discrete goals, right? That's fine actually, because when it comes to the style, like the style is actually continuous, and the robot keeps track of even like what style you're trying to pick up the object. So here I'm comparing these 2 cases where I'm starting with no assistance versus shared autonomy. And then once you're going for the goal, once you're you're using your low degree freedom for the goal, once the robot figures out what object you're going for, it can actually move the arm like closer and try to like go towards the red cup or the purple cup. And afterwards, what happens is if you're controlling, let me actually go to this slide. When you're controlling for preference, the robot, again, like in the shared autonomy setting, could help you like go for the correct preference that you really want to do. So what's happening here is the action that the human is putting in is this phi, which is based on the latent dimension, z, the current state, and the belief that the robot has. And then in the setting of shared autonomy, what's really happening is the action is just a combination of the action that the human is putting in addition to the action that the robot thinks it should be putting in. Then the action that the robot thinks should be putting in is based on the belief of what goal you're going for, basically. Yeah? All right. OK, so again, OK, does this work? Like, is there any reason for this to work? So the first thing is one can show that actually this idea of using this approach converges. So what that means is if I start from any state in the world, I could reach to any goal that I would want based on a set of bounds on what my control can do. So you can actually show that using Lyapunov stability. So what you can do is you can define your Lyapunov function to be the error squared, and error being the difference between your optimal goal you're going for and your state, right? So the derivative of the state is really the actions that you're taking. And what's the action you're taking? Well, the action that the robot is taking is a combination of user's control and what it's putting in as shared autonomy based on its belief of where the goal is. Okay? And then based on that, then you can actually compute the derivative of v and make sure that that is not going to be positive. So by doing so, the property that we basically need to ensure is that belief at the optimal goal times our error is going to be an upper bound for the bound of control input. So that's where the bound of control input comes in. And then how much your shared autonomy can take you to other goals. Okay? So one could define a set of bounds on that. So we're going to define sigma h to be a bound on the control input of the human. And we can define sigma r to be the maximum distance of any other goal to my current state. And then based on those, you can basically like make sure that your make sure that your approach, the approach we're calling it Layton Actions plus shared autonomy, is uniformly ultimately bounded stable, based on this delta value that we are defining, which tells us what's the radius of how close we are getting to the actual goal. Okay, so that's nice. Okay, so when I'm using this algorithm, yes.
Are you basically treating the human input as a disturbance to a controller that works by itself, or is it actually meaningfully stable to the human's input?
So yeah, no, so I'm treating it more as like a thing that's bounded. Yeah, so that's true. Yeah, for the analysis, we are treating it as yeah. So if the human input is completely off and it's like giant, like you're not going to be able to like bring your arm back in. Yeah.
But you just like the target to reflect the human's input at some point, right? This is like the robot is doing its thing. The human can't screw it up too much.
For the analysis of making sure that it converges. Yeah. Yes, yeah. For the analysis of making sure it converges, it's basically saying human input is not going to be like too off. For the actual thing, the human input could actually drive it to various goals. Yeah. Mm-hmm. Right. Okay, so that basically ensures convergence. In addition to that, one can change the loss function to add an entropy term, basically, to make sure that you can add exploration. So let's say that your robot arm, like let's say that your human makes a mistake, which happens all the time. So makes a mistake and goes to a different goal. And then now they want to back up and go back to the original goal. Your shared autonomy would be like, hey, I thought you were going for the purple goal. Like, what is happening? Like, why are you trying to back off? So in order to actually allow that, you're adding this entropy term here to the loss function to actually allow changes between the goals. So that's another kind of like technical thing that one can do to make this actually achieve different types of goals. Okay. And then finally, this is also another minor thing, which is this idea of introducing new goals. So if I train on a particular like reaching goal using Layton Actions and shared autonomy, if I introduce a new goal, I could actually do a transformation of my trajectory and be able to figure out what shared autonomy could do, like without basically retraining everything. Okay. All right. Okay, so let me actually show you how this works in practice. So we're comparing our approach with this approach called retargeting, which is from HRI 2017 from Belgia's group. And what they are looking at is this method where it's very similar to end effector control. The difference is they're basically minimizing the energy of the final configuration that you're trying to get your arm in. So it's similar to end effector control. It's a little bit fancier than end effector control, I would say. Okay? And in terms of shared autonomy, we're using this approach that I just talked about, which is introduced by Sid Srinivasa's group, and it's called like hindsight optimization in the case of reaching different types of goals. Okay? So, all right, so the retargeting task, what it is doing is we're trying to pick up this marshmallow here, and we're trying to then scoop it in the icing. So scooping should be this motion that you get, like, you should get back your style and then scoop the icing and bring the marshmallow. So scooping is really difficult. So this person is having a difficulty like doing the full-on scooping. So at the end it's like, OK, I just like stabbed it in the icing. That looks good to me. And then they bring it to the rice, and they should dip it in the rice, which is, again, similar to stabbing. And I don't know what type of food this is, so this is just like based on which food material and which one is easy to pick up. So it took 86 seconds to achieve the task. And one thing to notice here is this person wasn't able to really like get a hold of different types of styles that you're going to get at your end effector for different types of like motions like cutting or scooping or stabbing or picking up. So what happened was, in terms of alignment, it was almost like stabbing like throughout, right? So if it is close to 1, it means that we were doing the task of stabbing, and they weren't really like scooping. They were trying to scoop, but it wasn't really working. But using this approach that I was just discussing, like Layton Actions and shared autonomy, you're able to do a little bit of both. It's actually not that perfect. So when I watched that, I was like, is that really what we get? It's better. So it does a little bit of scooping. It does that motion, which is nice. And again, remember, this is like low-degree freedom control. Like, this is actually pretty difficult to do with low-degree freedom control. And then you dip it in the rice, and you bring it back. So you kind of see the switch between stabbing and scooping, right? The stabbing starts off because you stab the marshmallow, and then you want to scoop it in the icing. So stabbing goes down, scooping comes up. And then you kind of want to switch back again because you're putting it in the rice at the very end. So that's very similar to stabbing. So you kind of want to expect this type of behavior, and it does that. And it's shorter time too, which is nicer always. Okay. All right. Okay. So the key idea that I've been trying to talk about here is that in this case, what we're trying to do is we're trying to learn this low-dimensional representation conventions that are used by humans when they're controlling these robots, right? When they don't want to really deal with this high-degree control space. And robots, if they know that, if they know what the conventions are, they can actually bring in and add shared autonomy to it and try to help you like achieve this task a little bit more. And what we're really using at the end of the day here is a CVAE based on a set of loss functions that are necessary when we are thinking about these types of robotics tasks. All right. OK, so that was kind of this idea of teleoperation and what we can do in terms of understanding what it is that the person really wants when we are thinking about teleoperation. Now, what I want to switch to, so I have till 15 minutes. OK. So what I want to switch to now is basically thinking about the interaction in a dyadic setting where you have two agents, both of them are intelligent, both of them are trying to do a task. And I want to think a little bit about what conventions mean in these settings. So I'm going to start talking about, well, what does conventions mean like beyond this teleoperation setting? Like what can we call conventions when you're thinking about interaction? And then after that, I'm going to talk a little bit about this idea of influencing. Okay? So I started thinking about this problem a while back, and I still think it's a very interesting problem. And I know a lot of people have thought about this problem before too. So this is a problem of moving tables. Okay? So if you have two people who want to move a table together, they're able to do it, and I don't know how. I actually don't know how like people are able to do this. Okay? So you can blindfold these people, you can tell them to not use language, and you can just kind of force them to just use forces. And through forces, they're able to figure out how to move a table and which direction to move it and how to get the table to where it should go. Okay? Which is kind of crazy because it's hard to get robots to do that. Like it's really hard to bring in two robots and say, hey, robots, you're not talking to each other. Like no conversation, decentralized control. And there's an object in between, and you tell the robot, move the object in between based on the responses and forces that you're feeling from the other agent. That's actually pretty difficult. That's a decentralized control problem. Pretty difficult. Okay? So let's say that the setup, so we start looking at this robot problem. The setup is we have this rod, we want to put it on the table, and the robot in the back sees a set of obstacles. It sees these boxes. And the robot in the front sees another set of obstacles. It sees these books here. And together, they're seeing everywhere in the environment, but they have this partial observability too. Right? So through their forces, they need to like tell each other almost like where all the obstacles are to actually achieve the task. And if you do the most naive thing, you might say, well, I'm going to do independent control, meaning that this robot is going to do its thing based on what it sees, and that robot is going to do its thing based on what it sees, and that's not going to work, right? It's kind of clear like why it wouldn't work. Let's show a video of it. It wouldn't work because this robot only cares about the books. The other robot only cares about the boxes. They're going to do push and pulls that are going to cancel each other out, and then you end up hitting the obstacle. Okay. All right, so that doesn't work. So what should we do? So what's really happening is the robot here has an observation of the state, its own state, and this robot in the back has an observation of its own state. But the other thing that these robots have an observation is the actions of the other agent. They feel the pushes and pulls of the other agent. So the idea is, could we learn something about the pushes and pulls of the other agent? That's what humans do, right? Like humans kind of learned from these pushes and pulls of their partner. So could we do that? Okay. So but the reason that is hard in this particular setting is that interpreting the meaning behind your partner's actions is not really that obvious when it comes to this robot collaborative transport problem. Because the pulls and pushes that your robot is putting in can have many different reasons and many different meanings. So here's an example. So imagine you have your robot 2, and your robot 2 is pulling your arm in this particular direction, and it's putting this A2. So it can put this A2 because it just wants to go there, like because it just wants to like place the rod in that direction. So it's just exploiting the information. It could do that because maybe it's trying to actively give you information. So imagine there's an obstacle right here, and you don't know that, and the robot knows you don't know that. So it might actually try to like actively give you information and push you really hard in a different direction, so you don't hit his obstacle. Okay? Like if there's like a giant hole right next to me and I'm moving a table with someone, I'm going to push really hard in a different direction because there's an obstacle here. And I want to give information that there's an obstacle here, and I'm not hitting there. Right? Like I'm not like going to fall in the hole. Right? So I'm going to push really hard. And this is actually kind of interesting because this is something that people do all the time in terms of like using exaggeration or legible motion or expressive motion, which is something that we use like in HRI all the time. And this is legible motion is just an instance of this idea of active information giving. I'm actively giving you information, telling you, so you have a better estimate of what is happening in the world. And then the final reason for the same exact action could be for gathering information. So maybe I'll like nudge a little bit in a specific direction. Just see how you respond. Like how are you going to respond to that? Like would you be okay going in that direction? So the same pull that I would do, the same A2 could have many different reasons. And I'm using one channel of communication to kind of get across many different reasons for it. Okay, so that's pretty difficult to deal with. So what should we do? So in this setting, one way to deal with it is say, well, my robot is going to follow this decentralized policy, pi1, which is a function of the actions. In addition to that, it's going to be conditioned on its state and the actions of its partner. Okay? And well, what is that equal to? Well, that's going to be a thing that tries to match as much as possible a centralized policy. If both of us knew S1 and S2, then we knew everything in the environment, we could have achieved the task, right? So what this decentralized policy should do is it should try to match the centralized policy as close as possible, but subject to the fact that it has a belief over these unobserved states, the S2s, because it doesn't really know what S2 is. If it knew what S2 was, it could just like match the centralized policy. It doesn't. So it has a belief over that based on the actions of the partner. So it's trying to learn from the actions of the partner. Okay? So at the end of the day, you have this policy of agent 1 that depends on policy of agent 2. And you kind of get the classic like theory of mind problem here, right? Like the actions of your orange robot depends on the actions of your blue robot. The actions of your blue robot depends on the actions of your orange robot. And then you have the usual like infinite regress problem here. Okay, so that doesn't really work. I argued like at the beginning that's hard. That doesn't really work. That's not what people do. Okay. All right, so our idea here was, could we think about conventions again? Could we think about roles and conventions as a way of communicating with each other and giving distinct meanings to the actions that we take? So this might be a simple idea, but this is actually necessary. So what we show is conventions and roles is actually the necessary thing to break this symmetry So imagine a set. So what we are defining here is we're defining two types of roles. The first type is a leader role or a speaker role, which is basically any type of policy that only depends on your state. This is basically saying, I'm not listening to your actions. I'm just going to do the thing based on what I know. Okay? So this is more of a leader role. So that's trying to do active information giving. Basically, it's telling you, hey, I'm not listening, so here is all the information that I can give you. My policy depends only on my state. And the second type of role is a follower role. You can call it a listener role, which is basically any policy that takes actions based on the states in addition to the actions of the partner, which is basically telling you, hey, if I'm a follower, I'm trying to actively gather information about you, so I'm listening to you as much as possible, and my actions are in response to your actions. Okay? So what we show is these roles are actually necessary. So in a linear dynamical systems version of this, so not the robot version, imagine you have two linear dynamical systems that are kind of working together with literally x not equal to ax plus bu version of this. What we can show is you have to alternate roles to achieve the goal. Okay, so what we can show is if you have fixed roles, all your systems are going to become unstable after some amount of time. So you need to have alternating roles. And in addition to that, what we can show is that as you increase, and this is kind of like an obvious statement, but you can prove that, that as you increase the frequency of your alternation, you do get close to the behavior of a centralized team. So your decentralized team becomes close to a centralized.
May not be appropriate, but could you tell us what that linear model looks like?
Can I show you after the? Yeah. So this is a Coral paper. Yeah, so I can show you how that actually looks like. Yeah. All right. And then, and then another interesting thing is, so in these cases, the linear model actually doesn't have any noise, for example. So it's just x not equal to ax plus bu version of it. But if you add the noise, then for a specific type of noise, I think it was it's a zero mean type of noise, you can actually achieve the task by alternating roles. And better speakers are speakers that end up exaggerating. So remember I was talking about active information giving? So if you're exaggerating and you're using legible motion or you're using this exaggeration, you can actually convey this information. Okay? All right. So we decided to do this sharing control with switching roles, and this is the behavior that you would get from the robots. So in this case, the frequency of robot actions is 1 per 1,000. So it's 0.001 seconds. And the frequency of switching roles is about 0.5 seconds. So every 0.5 seconds, they're switching roles. Okay? And they're able to move the rod to the right location on the table. Yeah. So maybe it was obvious that having roles is important. After the fact, when I looked at this, I was like, okay, that makes sense. If you tell me what you're doing, if you're telling me you're a speaker and I'm telling you I'm a listener, we should be able to do this. But the interesting thing was you have to do this. You actually have to do this. And this is kind of what humans really do when they're doing these negotiations, when they're moving tables. If they're pushing in a specific way, they're trying to signal you that, hey, I'm leading now, or they're trying to signal you that I'm listening now. And one interesting thing to do, which we didn't really do here, is thinking about learning these conventions directly, right? We're setting a fixed policy, a fixed change of roles here, but one could try to actually learn those. Okay. So this is just the resistance forces. So you can kind of see with the roles, there's not that much resistance in a specific direction between the robots, but without roles, you actually get resistance between the robots. All right. So let me just to wrap up quickly. All right, so the key insight here was that humans are basically implicitly communicating with each other through their actions, and specifically through these low-dimensional things, signals like leader-follower roles. And one idea is basically trying to communicate these roles to actually, and learn from your partner's actions to actually achieve a task that is kind of this collaborative transport task. I'm going to skip this, but just briefly, another place that roles show up is in language. So that's also something that we are looking at. I'm getting more and more interested in the intersection of NLP and HRI, which is pretty interesting, where you're thinking about the repeated interactions between agents and how over repeated interactions, humans end up creating reductions, and I'm calling reductions the convention that's being built here over repeated interaction. So in this case, if you're referring to this image, maybe the first time you're referring to it, you might say a man is playing with a frisbee, and then over time you might just call it frisbee. And I would call that also as a convention that's built over time between the two agents, a reduction that you kind of see in language. So that's a separate talk, but I just wanted to briefly mention that roles show up there too. Okay, so I don't really have time that much to talk about influencing, but I just want to leave you guys with some thoughts on the idea of influencing. So I started talking about how humans interact with each other, right, and how they can also influence each other. And robots should also reason about how they should influence humans. And we've seen that in driving, right? Like in the driving work that I was showing earlier, like the idea there was the robot is going to nudge in and influence the actions of the other driver and make the other driver slow down. So I think influencing is pretty interesting. And in this case, we were modeling this as a theory of mind approach where you're influencing the actions of the other agent. But one thing that you could do is you could think about conventions and influencing the conventions directly instead of influencing the direct actions of the person. Okay? So just one fun example was, let me just end with this one fun example. So here we have a robot. So this is more of a, think of it as an example. And the robot is supposed to bring these cans of soup to the recycling bin. And if you trust the robot and you think the robot is doing the right thing and is basically there to help you, then you kind of expect the robot to follow a trajectory that is a straight line trajectory. So that is kind of like, so that is kind of like this. It goes to the can, and it picks up the can, and just brings the can to the recycling bin. So you kind of expect it to follow a full-on straight line and do that, because it would do like shortest path, like least energy. That is kind of expected, right? So if you're interacting with this robot, and the robot comes out and does a different trajectory, maybe it follows a trajectory that kind of looks like this. It drops the can of soup and brings it back up to the recycling bin. In that case, like, what would you think, like as a human? Why is the robot doing that? It drops it and then brings it back up. It's fine.
It's heavier than expected.
Yes, you would think the object is heavier than expected, right? So that's good. If the robot knows that, right? If the robot knows that it can actually bring the can of soup down and bring it back up and do that trajectory, and you would think that the object is heavier, then it can actually use that knowledge, right? So it's a little bit of trickery, I would say. But what the robot can do is the robot can take a set of actions. The robot could optimize for its own reward function, which might be very different from your reward function. It might optimize for its own reward function based on its actions and state, and based on the fact that you're following a model that's trusting the robot. You're following a model where you have a belief over what the robot can or cannot do, and the robot can influence your belief of what the robot can or cannot do. So again, think of this as a convention. The robot can actually influence that convention and influence how you're thinking about this robot. So you might say, oh, that's tricking. Like, I wouldn't really want my robot to do that. But I would argue that there are scenarios that you might actually want your robot to do that. So one scenario, I guess, again, is in the assistive setting, or if you have exoskeletons, where the robot is trying to help you learn how to walk again, let's say in a rehab setting. So in that setting, if the robot is doing all shared autonomy, like I was showing earlier, right, if it's putting all the control in and doing all the work for you, you're not going to learn again, right? You're not going to learn how to walk again in this case. So in these settings, you do actually want the robot to have a different objective and optimize for that different objective and maybe trick you into doing different types of things. And maybe it can use the idea of conventions and influence you through conventions. So with that, I want to just mention that humans tend to influence each other based on their estimate of their conventions that exist, the shared representations, the shared conventions that exist between them. And in general, when we are thinking about robots interacting with humans, they should also think about how they can positively influence people. And I think that does bring up a set of other questions that Richard actually talked a little bit about. One direction, again, just leaving you with this one thought out, is this direction of adaptations, which I think is pretty interesting. So I used to live in San Francisco until a few months back, and there are this particular company there driving, and they get stuck at intersections a lot. So what happens is when I see these vehicles, I just go around them. When I'm biking, like in the SF, I just go around them, because when I see them, I'm like, this car is probably stuck there, so I'm going to just go around it. So it's kind of interesting that my behavior has changed based on maybe like, 3-4 interactions that I've had with this car. And I've decided to change my behavior and just go around this vehicle. I'm giving wrong data to them, because they're going to think, oh, humans are always going around me. Good. That's my model of humans. And it's kind of interesting that human models like change and adapt here, right? So I think one thing that would be interesting to think about is most of our work in modeling humans, imitation learning, human-robot interaction, assumes humans are stationary. And we model humans, we model these conventions, and just go from there. But humans change. They're not following a stationary model. And we should think about these changes in the human behavior and influence them in particular ways. And then that, again, I think brings up this idea of conventions. There are different driving conventions in different countries. And those conventions are built because we have these repeated interactions. And throughout these repeated interactions, we adapted, and our behaviors change, and we ended up in very different equilibria. If I'm driving in Palo Alto versus Tehran, very different story. But both of them work. Both of them work great. It's just different equilibria that you get. So with that, I think it would be interesting to think about adaptations when we have repeated interactions too. Thank you. All right, thank you, good, and thank you guys.